A fast-moving object the size of Manhattan is hurtling towards our solar system, and it will make its closest pass to Earth on December 17th. Comet, asteroid, or something else?
Something just changed in the data coming from deep space, and scientists can't explain it.
It is only the third time we have detected an object that has come from beyond our solar system.
The final signal from 3I Atlas, our newest interstellar visitor.
From images, we also saw that this object is active, which is an indication that this object is in fact a comet.
Looks nothing like anything seen before. It's weak, fading, but it carries a strange pattern that has the world's top observatories on edge. This isn't just another comet passing by. It's leaving a message, and everyone's racing to decode it. 3I Atlas, the third interstellar visitor. 3I Atlas is a frozen visitor from deep space, the third object in history confirmed to have come from outside our solar system. Before this, we had only seen two others, Oumuamua in 2017 and Borisov in 2019. And now, in 2025, a new wanderer has arrived.
It is only the third time we have detected an object that has come from beyond our solar system.
The story began on July 1st, 2025, when a telescope high in Chile caught a faint moving dot of light. It was part of the Atlas Sky Survey, a project that scans the heavens every night for anything new or unusual. When the astronomers traced this object's path, they realized instantly that it was special. It wasn't looping around the sun like an ordinary comet or asteroid. Instead, it was flying in on a one-way route, in from the deep, around the sun once, and then gone forever.
For that distance from the sun, this is really exceptional. You have to be an interstellar object to be going that fast at that distance from the sun.
That kind of path is called hyperbolic, which simply means the sun's gravity can't hold on to it. Normal comets circle back again and again. This one doesn't. Its speed alone gave it away as an outsider. Far from the sun, it cruises at about 130,000 miles per hour. And as it dives closer in, gravity pulls it even faster, up to around 150,000 miles per hour near its closest pass. That's fast enough to travel from Earth to the Moon in under 3 hours. No object born in our solar system moves quite like that unless it's getting ready to leave for good. Within a day of discovery, observatories around the world confirmed it really was interstellar. NASA posted the key details: no danger to Earth and plenty of room to spare. The comet would stay well over 170 million miles away from our planet. And even at its closest to the sun, it would still be about 130 million miles out, roughly the distance between the sun and Mars.
That's going to be barely inside the orbit of Mars, and then it's going to keep going on its way out of the solar system.
Think of the solar system as a racetrack. Earth runs in the inside lane. Mars is a little farther out, and this newcomer just brushes the edge of Mars's lane before heading back into open space. No threat, just a spectacular flyby from a true visitor. Over the next few months, the timeline of its visit unfolded like clockwork. It was spotted in July, photographed by the Hubble Space Telescope a few weeks later, and by late August, another telescope in Chile called Gemini South captured it, sprouting a faint tail, a classic sign of a comet coming to life. By early October, it swept past Mars from a comfortable distance of about 18 million miles. It will reach its closest point to the sun around the end of October and will fade from view by the end of the year as it sails back into the stars.
It will be closest on October 3rd, and spacecraft in orbit and on the surface will try to catch a glimpse.
What does this traveler look like? Imagine a glowing cotton ball shape drifting across the black sky, its heart hidden inside a hazy shell of gas and dust. That fuzzy glow is called the coma, and it forms when sunlight warms the comet's icy surface, turning frozen gases straight into vapor. The vapor streams outward, carrying dust with it, and sunlight pushes that material into a tail that can stretch for thousands of miles. Unlike Oumuamua, which looked like a bare rock and never grew a tail, 3I Atlas behaves exactly like a classic comet. Hubble's photos showed a soft, teardrop-shaped glow around a small central body, and ground-based telescopes later caught a clear tail spreading behind it. It's the kind of activity scientists expect from a comet, rich in icy material. The solid core hiding inside that glow, what scientists call the nucleus, is much smaller than the halo surrounding it. Early estimates suggest it could be anywhere between 1/3 of a mile and about 3 miles wide. That's the difference between the size of a large city park and the size of a small town. But what we actually see in photos is mostly the shimmering cloud of gas around it, not the rock itself. Then came the real surprise: its chemistry. When the James Webb Space Telescope turned its gaze toward 3I Atlas, it split the comet's light into a rainbow to see which gases were hiding inside. What Webb found was astonishing. The comet's cloud was overflowing with carbon dioxide gas, along with traces of water vapor, carbon monoxide, and a faint whiff of sulfur compounds. The balance between these gases told a fascinating story.
It is only the third time we have detected an object that has come from beyond our solar system.
Most comets near the Sun are dominated by water vapor, but 3I Atlas is different. Its carbon dioxide level is one of the highest ever seen in any comet. That single fact is a huge clue about where it was born. In a young planetary system, ices form at different distances from a star depending on temperature. Water ice freezes closer in, while carbon dioxide freezes only in much colder regions farther out. So if a comet is loaded with carbon dioxide, it likely formed far from its home star, maybe at the icy edges of its original solar system. Another possibility is that it has surface layers that trap water, but let carbon dioxide escape more easily as it warms. Either way, it hints at a birthplace in deep cosmic cold. NASA's Sphere-X mission added another piece to the puzzle. It detected strong signs of water ice mixed with an unusually wide cloud of carbon dioxide gas. That means this comet doesn't just puff out a little carbon dioxide, it's streaming it far into space, forming a massive, ghostly halo even while it's still far from the Sun. Most comets wait until they get much warmer to do that. But 3I Atlas started leaking early, proof that its ices are made of very volatile material that turns to gas even in the chill of deep space. The chemistry gives scientists a window into its origin, but the direction it came from adds even more intrigue. By mapping its motion through the sky, researchers traced its incoming path and compared it to the way different groups of stars move through the Milky Way. The numbers suggest it may come from what astronomers call the galaxy's thick disk, an older population of stars that sits above and below the flat spiral where our Sun lives. If that's true, this comet could be older than our solar system itself. Some models estimate it may have formed 7 to 10 billion years ago, back when the Milky Way was still young and star formation was at its peak.
Dust being pushed back behind the object by the solar radiation pressure.
A period scientists nicknamed the galaxy's cosmic noon. That means 3I Atlas may have been wandering the galaxy for billions of years before we ever existed, carrying in its icy core a chemical memory of the time before our Sun was born. We know what 3I Atlas is and where it's headed. Now it's time to talk about the data that truly counts, the final signal. The final moments of 3I Atlas. Right now, scientists are racing the clock. Every window to watch this interstellar visitor is brief, and each one closes faster than the last. The first of those precious opportunities opened around the start of October, when 3I Atlas swept close to Mars's orbit. From there, the red planet suddenly became the best seat in the solar system.
It will be closest on October 3rd, and spacecraft in orbit and on the surface will try to catch a glimpse.
Its orbiters, machines like NASA's MAVEN, the European Mars Express, and the ExoMars Trace Gas Orbiter, carry exactly the instruments a comet researcher dreams about. MAVEN, short for Mars Atmosphere and Volatile Evolution, has a powerful ultraviolet spectrograph, essentially a camera that doesn't take pictures but listens for the faint glow of atoms in invisible light. When sunlight hits a comet's escaping water vapor, it breaks those molecules apart into hydrogen and oxygen. Each of those atoms glows in ultraviolet light at a specific wavelength, a telltale shimmer that MAVEN can catch from millions of miles away. Back in 2014, MAVEN used that same trick to study another comet, Siding Spring, as it brushed past Mars and wrapped itself in a giant hydrogen cloud. Now, scientists are running the same play again, hoping to see a ghostly halo of hydrogen and oxygen forming around 3I Atlas as its ices vaporize in sunlight. ESA's Mars Express spacecraft joins the hunt from another angle. It carries instruments called SpyCam and Omega, which specialize in reading the fingerprints of molecules in both ultraviolet and infrared light. The ExoMars Trace Gas Orbiter adds two more, NOMAD and ACS, a pair of extremely sensitive spectrometers designed to sniff out faint gases in Mars's atmosphere. Here, they're being turned toward the comet. If 3I Atlas is venting water, carbon dioxide, carbon monoxide, or even cyanide-bearing compounds, these spectrometers can pick up the signature, thin colored lines hidden in the sunlight reflected from its coma. Together, these orbiters form a kind of remote laboratory in Martian orbit. They can measure not just what's leaking from the comet, but how fast it's changing from night to night. Imaging cameras can track the cloud of dust and gas, watching whether it swells smoothly or bursts into jets. Even simple brightness readings help scientists learn whether the comet's activity is steady or pulsing. It's like watching a breathing pattern from millions of miles away.
For images, this is a brand new near-Earth asteroid.
The timing couldn't be better, or worse, depending on where you sit. While Mars has this clear view, Earth does not. From our planet's position, 3I Atlas is slipping almost directly behind the Sun, which makes it practically invisible to our telescopes. When an object is too close to the Sun in the sky, the glare overwhelms even the most powerful optics, and most observatories have to pause their tracking until it swings back out. But spacecraft orbiting Mars don't share that problem. They sit at a different angle, far enough from the Sun's blinding light to keep their instruments safe, but close enough to catch valuable data. That's why October around Mars became such a critical window, one of the few moments when high-quality ultraviolet and infrared readings could be made while Earth-based telescopes were effectively blind. Then comes the main event, the comet's closest pass to the Sun, known as perihelion, around the end of October. This is when sunlight hits hardest and the ices boil the fastest, turning the coma into a luminous, expanding shroud. But here's the problem. When that happens, Earth is still in a terrible position.
The physical makeup of an object tells us about its capability, its impact potential. What can it do on the Earth?
The comet will lie only about 13 degrees away from the Sun in our sky. That's far too close for most telescopes. And even for space observatories like the Hubble and James Webb, it falls into their do not point zones. Those giant mirrors must never stare near the Sun's brightness, or their optics could be damaged. So while the comet reaches its most dramatic phase, almost all of Earth's major instruments must sit quietly, waiting. This is when a different kind of spacecraft, ones that are designed to look directly at the Sun, take center stage. The Solar and Heliospheric Observatory, or SOHO, has spent decades staring at our star, blocking the Sun's blazing disk with a small metal mask so it can see the faint solar corona around it. Occasionally, a comet passes through that field of view, trailing a tail that seems to grow in real time. The European Space Agency's Solar Orbiter and NASA's Parker Solar Probe have similar wide-field imagers that might just catch 3I Atlas as it skims past the Sun.
The more data we get, the better we can measure the position of this object as it travels through the solar system and it moves.
ESA's early predictions are cautious. SOHO's cameras cover a wide area, but the comet may be too faint to stand out against the solar glare. Still, even a single detection, One frame where the comet's tail curves or brightens would be valuable. It would show how violently it was shedding dust and gas at the moment of maximum heating, when every other telescope was forced to look away. For comet science, that single snapshot would be priceless. As 3I Atlas swings past the Sun and begins heading outward again, the geometry shifts once more. Now the view opens up for spacecraft farther from Earth, and this time the spotlight falls on ESA's Jupiter Icy Moons Explorer, better known as JUICE. Between early and late November, roughly from the 2nd through the 25th, JUICE will train its cameras and spectrometers on the fading comet. By then, 3I Atlas will still be active, but no longer lost in sunlight. The tail will likely stretch for millions of miles, the dust cloud still dense enough to reflect sunlight, and the gases still glowing in infrared and ultraviolet. Over several weeks, JUICE can watch how quickly that activity declines, how the gas fades, how the dust grains change size, how the coma shape evolves as the spinning nucleus slowly cools. It's a rare chance to film an interstellar visitor catching its breath after a close brush with our star. And JUICE isn't alone in this chase. NASA's Psyche spacecraft, launched to study a metal-rich asteroid, happened to pass within about 28 million miles of the comet's path in early September. That's not close enough for a detailed flyby, but it's close enough for opportunistic science. Even a basic brightness check or a dust monitor reading could add another piece to the puzzle.
From images, we also saw that this object is active, which is an indication that this object is in fact a comet.
Later, as the comet's tail stretches farther into the outer solar system, other spacecraft may drift through faint wisps of its material. If any of them detect a spike in dust or a small change in charged particles at just the right moment, that would count as a direct sample of 3I Atlas's trail, an accidental encounter worth its weight in gold. Those observations aren't just chemical trivia, they're clues to the comet's birthplace. The story doesn't stop with chemistry. The light itself carries information about rotation. As the comet spins, its bright spots, regions releasing gas or reflecting sunlight, rotate in and out of view, making its total brightness rise and fall in a repeating rhythm. By tracking those fluctuations over many nights, scientists can deduce the rotation period, like timing the spin of a distant lighthouse. If the pattern repeats smoothly and consistently, it's a sign of a natural, irregularly shaped nucleus. If it were to blink in a perfect mechanical rhythm regardless of viewing angle, that would raise eyebrows. But so far, 3I Atlas behaves exactly as a normal comet should. Its brightness changes gently and irregularly, governed by its spin and sunlight, not by any unnatural timing. Another piece of detective work involves motion. When a comet vents gas, it behaves like a weak rocket that can shift its orbit ever so slightly, a phenomenon called non-gravitational acceleration. Astronomers measure this by comparing thousands of position readings against the orbit that pure gravity predicts.
It's partially due to the size of the object, but also it's partially due to the activity, and so we cannot really pinpoint.
With the mysterious Oumuamua, that slight drift caused endless debate because no visible coma was ever seen. In contrast, 3I Atlas's orbit fits the data almost perfectly. If there is any extra push from its outgassing, it's tiny, so small it fits comfortably within normal comet physics. That steadiness reinforces the idea that we're looking at a heavy, stable nucleus behaving naturally, not an object being mysteriously propelled. Still, timing is everything. With such short viewing windows, scientists have to squeeze every drop of data out of each observation. They talk constantly about something called signal-to-noise, or SN. It's the ratio of the whisper you're trying to hear to the background static you're fighting through. To improve it, you either get closer, quiet the noise, or listen longer. In practice, that means pointing telescopes when the comet is highest in the sky, stacking multiple exposures to average out random noise, and repeating the same measurement across several nights. If both Mars Express and the Trace Gas Orbiter detect the same chemical change on the same night, that agreement makes the signal stronger. If JUICE later observes those gases fading at a rate that matches the drop in dust brightness, the confidence grows again. Real science builds on consistency across instruments, not one-off flashes. When perihelion hits, the comet's tail will be slammed by the solar wind, a stream of charged particles flowing outward from the sun. That interaction can twist or ripple the tail within hours. Instruments on SOHO and Solar Orbiter are built to see those delicate changes close to the sun by blocking out its central light. If 3I Atlas is bright enough in their fields of view, we might actually watch the tail bend and flutter as the solar wind pushes against it. Even if the cameras see nothing, that result still helps. It sets an upper limit on how bright and dusty the comet could have been at its most intense moment. By December, when it passes its closest point to Earth, about 170 million miles, it will be too faint for casual stargazers, but still within reach of the largest observatories.
At a velocity of about 135,000 miles per hour, so it's going really fast. For that distance from the sun, this is really exceptional.
JUICE will likely wrap up its campaign around that time, leaving the rest to ground-based telescopes as the object drifts toward the region of Jupiter's orbit and beyond. The data gathered over these few months will be studied for decades, not just to understand 3I Atlas, but to refine how we recognize the next one. Because somewhere out there, in the deep between stars, more of these icy messengers are drifting silently toward us. But where are these wanderers really coming from? The mysterious place our visitors call home. Out beyond the last planets, beyond the reach of our sun's magnetic breath, lies a region so faint and so quiet, it's hard to believe anything can cross it. Yet every interstellar visitor we've ever seen, Oumuamua, Borisov, and now 3I Atlas, comes drifting through that same invisible ocean. The only reason we even know what that place feels like is because of two small, aging travelers that left home decades ago and never came back, Voyager 1 and Voyager 2. They were launched in the late 1970s to tour the outer planets, but long after their cameras stopped sending postcards of Jupiter and Saturn, they kept flying outward.
The launch was way back in 1977. The arrival was announced today.
Decade by decade, they pushed farther from the sun, until, at last, they reached the edge of its domain, the border where the sun's power ends and interstellar space begins. To picture that boundary, imagine the sun as a campfire that never goes out. From that fire, a steady wind of charged particles, mostly electrons and protons, blows outward in every direction. That solar wind fills a vast, teardrop-shaped bubble around the planets, a protective shell called the heliosphere. Inside it, everything is soaked in the sun's magnetic field and plasma.
That happens because of this invisible field called a magnetic field. The sun has a magnetic field.
But at some distant point, the wind runs out of strength. It slows, compresses, and finally yields to the thin gas that drifts between the stars. That fragile skin, where one realm gives way to the other, is called the heliopause. Cross it, and you've officially left the solar system. Voyager 1 reached that invisible line first, on August 25, 2012. By then, it was more than 11 billion miles from the sun. So far, that radio signals from Earth took over 17 hours to reach it.
Now 11 billion miles from the sun, it's approaching the outer limit of our solar system.
The proof that it had crossed came not from pictures, but from sound. At least, sound turned into numbers. Its instruments detected plasma waves vibrating around the craft. Scientists converted those oscillations into tones we could hear, and realized the pitch had suddenly jumped. The surrounding electrons were roughly 20 times denser than they had been inside the bubble.
We're on a journey to the edge of the bubble the sun creates around itself.
Voyager 1 had stepped into a heavier, colder sea. 6 years later, on November 5, 2018, Voyager 2 followed and recorded the same shock. a sharp spike in plasma density the moment it passed beyond the sun's reach. Together, the two crafts gave us the first direct taste of the space our interstellar guests call home. So, what exactly is out there? It begins with a breeze, not the kind you can feel, but a flow of gas and dust that our whole solar system is drifting through.
And it began to feel the thin gas particles that lies between the stars, the breeze of interstellar space.
Astronomers call it the local interstellar cloud, a patch of warm, tenuous matter drifting through the Milky Way. Our system moves through this cloud at about 25 miles per second, roughly 56,000 miles per hour, from the direction of the constellation Scorpius. You could call it the interstellar wind. It is hot by physical standards, somewhere between 7,000 and 10,000 Kelvin, yet so thin that, compared with any air we breathe, it is almost a perfect vacuum, more like a ghostly mist than gas. The Voyagers, along with Earth-orbiting missions such as NASA's IBEX, helped measure that ghost in detail. The electron density is just a few hundredths of a particle in each cubic centimeter. The magnetic field threading through it is faint beyond imagination, only a fraction of a nanotesla, far weaker than the field of a cheap refrigerator magnet. And yet, that weak field shapes entire cosmic neighborhoods, guiding charged particles and sculpting the sun's bubble like a gentle hand on water. Then, in 2017, Voyager 1 began hearing something remarkable. Its long antennas picked up a faint, continuous tone, a slow, steady hum coming from the plasma around it. The frequency shifted over time, sliding higher or lower as the local density changed. It wasn't a burst from a solar storm or some passing shock wave. It was a constant background melody. Scientists realized they were hearing the interstellar medium itself, singing softly as its charged particles vibrated. It was the first time humanity had ever heard the space between stars in real time. You could imagine it like this. Voyager 1 was a ship sailing across a dark sea, and at last, the instruments were sensitive enough to catch the sound of gentle waves brushing its hull. That hum, still monitored today, tells us that interstellar space is not silent. It's alive with ripples and turbulence, the slow breathing of the galaxy's plasma ocean. So, the sea is warm, thin, and humming. But where do the travelers drifting through it come from? Every interstellar object, Oumuamua, Borisov, 3I Atlas, and the countless others we might never see, is essentially debris from other people's planet factories. When a young star forms, it is wrapped in a disk of gas and dust. Inside that disk, grains collide, stick, and grow. Pebbles become boulders. Boulders merge into icy worlds that one day might become planets. But planet formation is messy. Giant planets migrate inward and outward, slinging smaller bodies around like billiard balls. Binary stars tug violently on each other's disks. Nearby suns in dense stellar nurseries pass close and disturb everything. The result is cosmic chaos, countless icy and rocky objects flung out of their birth systems entirely. Computer simulations show how efficient this process is. As massive planets shuffle around, they can eject tens of Earth masses of material into interstellar space. If a system has two suns, that ejection becomes even easier. Gravity does the work for free. Add in the gravitational bumps from passing stars in a crowded cluster, and you end up with a galaxy filled with cast-off worlds. When astronomers discovered Oumuamua, they realized something startling. If we managed to spot one so quickly, it meant there must be many more out there. Calculations suggested that within each cubic astronomical unit of space, a region the size of the Earth's orbit, there could be roughly a fifth of one such object at any given time. That may sound small, but across the enormous volume of the solar system, it translates to thousands of Oumuamua-sized wanderers drifting silently between the planets, most so dark and faint that even our largest telescopes can't see them. That number is staggering. It implies that nearly every star in the Milky Way has been shedding debris for billions of years,
The collision of the Milky Way galaxy with the Andromeda galaxy.
filling interstellar space with a blizzard of frozen fragments. Each one carries a chemical fingerprint of the world it came from. Some are rich in ices and behave like classic comets, while others are dark and dry, resembling asteroids. Not every ejection story is the same. Sometimes a giant planet captures a fragile comet and tears it apart before flinging the fragments outward. Those shards may lose their surface ice, leaving behind a rocky body that looks inert, something like Oumuamua. Other times, the body escapes intact, carrying reservoirs of frozen carbon dioxide, methane, and water, ready to vaporize when it passes near another star. That could explain why Borisov and 3I Atlas behave like normal comets, with tails and come.
Comets were these things that came from further out, and when they got near the sun, they'd warm up and volatiles would start to give off gases and they'd have a tail.
And the manufacturing never really stops. Even aging stars at the end of their lives can contribute. As they swell into red giants and begin shedding their outer layers, they can release whole clouds of ancient comets, sending one last wave of small bodies drifting into the interstellar sea. Thanks for watching. Now check out the videos popping up on screen for more unbelievable stories.